roll it. May I have 2 volunteers for this lab activity? Jonathan and Stokely. I know, you do have to be quick with that. Okay. Would you guys come up here, and would you each hold one of these? Stokely, would you hold this one? And hold it up horizontally, please. And Jonathan, would you hold this one and hold it horizontally, please? Very good. So we have these are our force plates, and we will be doing that, but not for a while. Does anyone see which is Jonathan holding, the blue or the red? He's holding the blue because as I lean into this, yeah, the value here. Is it really true that something is exerting minus 130 newtons on Jonathan's force plate right now? No. Why does it say that there is? Ben?
Resting down and someone turns it off.
Yeah, there's some calibration. I need to zero it. I need to tear it. So let's see. I bring that, and I want to tear 0 of them. So hold them precisely, I guess, straight up like that. Boom. And ha. Now, would you set yours down, Jonathan? And yeah, that's right, is what. See how when I pushed on it, it uncalibrated to the tune of about 20 newtons? How much is 20 newtons? Can you make 20 newtons a relatable amount of force for me, Andrew?
I mean, actually, like, isn't it, because you set it on the ground, now it's like, gravity's exerting force on it, and so...
Ah, that's true. That's actually a really good point.
Should we zero the
Yeah, so I guess now, I should have compared it to this. Would you hold that again? Now let's look at the calibration error, and you're right, it's actually quite a bit less. What is the approximate mass of that force plate? Anyone tell me? Jay? It was about 2 kilograms. That's right, because I had failed to realize that when it was reading 20 newtons, that was actually due to the normal force by the ground up on the force plate, and that normal force for what turns out to be a pretty well-calibrated force plate was the gravitational force for a 2 kilogram object. 20 newtons. How much is 20 newtons? It's the gravitational force that you'd experience with a 2 kilogram object. I had hoped to demonstrate that pressing with a large force on these force plates can cause the calibration to go off a little bit. Yeah, we'll do that later. All right, so I'm about to press play, and when I do, what I'd like you to do is actually, would you put them together now, but don't push very, very hard. Just push a little, with a little bit of constant force, okay? And I'm going to start it rolling, and once it is rolling, I'd like you to press harder, but still not so hard that either of you accelerates. This is not a competition. All right, so pressing a little bit. Great. And now press more, please, but still don't. All right. And now a little bit less, please. Thank you. Pause. Let's look at this, and let me auto scale it. That's pretty good. Notice the difference in their calibrations right about now.
Well, Jonathan's holding it down.
Well, yeah, could you hold it up?
Vertically, it should be on.
So still, yeah, see how it sometimes goes up to like 6? They can be as much as 10 off just due to random fluctuation. What do you see here in this graph? It's like they're doing the same thing. Does one of them clearly lead and the other one clearly lag? You know what I mean by leading and lagging? One happens first and then the other one happens later?
They're kind of moving. They're kind of like going at the same thing. Just red seems to be pushed a little harder.
Yeah, it looks like red tends to have a little bit of a higher value. That's true even for these lower values here. And so I would tend to assert that plus or minus a calibration arrow, they track each other extremely precisely. Even like the little things that look like noisy wobbles are reproduced between the two graphs and pretty darn at the same time. Is that fair? Okay. That maybe isn't so surprising, given that what we saw in their experience was symmetric. Neither of them did a thing that the other one didn't do. Okay, next, I'm going to have a run where I ask you to push your force plates together. So put them together now, actually, if you would. And I'm going to start collecting, and when I say go during the collection, I'd like, Stokely, for you to push hard enough to accelerate the Jonathan Stokely force plate system that way. So if this were a contest, I'm asking Jonathan to throw this contest and for Stokely to win it. But don't do that until I say go. And go. Okay, thank you. Okay, so let's look at this. What do you see? They are really close, like plus or minus a calibration error, even the little jiggles. Was the experience of Stokely's force plate very close to the experience of Jonathan's force plate in terms of what you saw? I don't think so. Like, Stokely's force plate won. Sure?
I mean, but it didn't seem like Jonathan was really accelerating a lot. Or like, it didn't seem like maybe they were moving in a specific direction, but it didn't seem like they were moving in that direction, accelerating.
Let's try this. I think that's a really good point. I'll ask for you to trade off who's winning. So keep your feet on the ground, but let's have like Jonathan accelerate the system this way and then Stokely accelerate it that way. Keep your force plates in contact the whole time. Let's see what that looks like. And I'll say go, hold on, go.
Oh, there we go. We can see.
What do you see?
So it's definitely a lot more separated than any of the other ones have been.
Is it clear that red is greater than blue is greater than red is greater than blue is greater? Red?
I'd say yes, when, well, as clear as it can be, when Stokely was pushing more and Jonathan was receding,
Mm-hmm.
red is above blue, and then when Jonathan was pushing back and Stokely was receding, blue is about above red.
What is the difference between their readings right now?
No, they gotta hold them straight up. They should be pretty even.
They are holding
Jonathan was
approximately.
Yeah, they're off by, I would say, 5 at a given moment. Here, I think we saw that Stokely was winning. Here, Jonathan. Here, Stokely, right? Here, Jonathan. I'm not sure I see from this that the winner's force plate was registering more force. I think it is true Stokely's read more here, and this is one where Stokely's where Stokely was causing an acceleration towards Jonathan. Here, I guess blue exceeds red there by a few, red exceeds blue by a few here. Here, this should be a Stokely victory, but I'm not sure we see a clear red exceeding blue. And I'll also note to you that even the wiggles seem to track each other quite precisely. Griffin?
The force plates didn't go through each other?
I'm sorry, say again?
The force plates didn't go through each other?
They definitely didn't pass through each other. Their electron clouds repelled robustly. This is an imperfect demonstration, but I wonder if you could have some sympathy for the following assertion. The force that Stokely's plate exerted on Jonathan's plate was pretty much the same as the force that Jonathan's plate exerted on Stokely's plate, no matter who was accelerating or whether the system was at rest. Ben? Why should that be true? Remember what I compared force to earlier today, Fred? When you had raised the idea of whether the ground's force on the legs would be the same as the legs' force on the torso. I said, force isn't a conserved substance. It's more like a, yeah, it's an interaction. And if I'm having a conversation with you, you're having the same conversation with me, right? Such is the nature of interaction. So I'll appeal to that sensibility too, as I assert Newton's third law. So go ahead and take a seat, and I'll talk a little bit about Newton's third law here. Okay, Newton's third law. Second law is combination of forces acting on a mass. First law is balanced forces, constant velocity. Third law, if object A exerts a force on object B, then object B exerts a force on object A, and those forces are the same type of force, in this case both normal. They're the same magnitude and they're opposite direction. What word have I not used in the last minute? It's true, I haven't used acceleration. I haven't used equal, it's true. Do you notice how does popular parlance talk about Newton's third law? Yeah, action and reaction. And I'm going to very studiously avoid action and reaction as I talk about Newton's third law. This is not about actions and it's not about reactions. We noticed that the forces were happening right at the same time. One did not lead and the other lag. If I'm having a conversation with you, you are having that conversation with me at the same instant. It's not like the action of my conversation with you causes the reaction of your conversation with me. I won't use action and reaction. If you do, it'll be because you've heard it hundreds of times in popular English, but we won't relate Newton's third law to actions or reactions in this class. Would you please draw a free body diagram of the block and of the table for this system where the block rests on the table? So two separate free body diagrams. So a block is resting on a table. Please draw a free body diagram for the block and then a separate one for the table. Let's see. Okay, so there's a table, and it's on the ground, and there's a block. Help me draw a free body diagram of the block, please. Stokely?
Gravity down.
Yep.
And then natural force.
Not a natural force, but a...
Not natural.
Quite all right.
Normal force.
Happens to thousands and thousands of people. Same size, bigger than, or smaller than? How do you know?
There's no acceleration.
Yes, good. All right, and a free body diagram for the table, please. Mass of the table. Ben?
Force of gravity, and then again, just a natural force.
Not a natural force, but a...
Normal force.
Okay, quite all right. Nope, happens to the best of us. Great. How big should I draw the normal force?
It's only because same.
Same? I think we're not quite done, actually. Would you Newton's third law me the end of this sentence? And by the way, what object exerts, forget what I just said, what object exerts this force on the block? Earth. Earth on the block. What object exerts that normal force on the block? The table. What object exerts the gravitational force on this table? Earth. Earth on the table. And what object exerts this normal force on the table? call it the ground, sure. The table exerts an upward normal force on the block. So, Newton's third law mean. Andrew?
The block exerts a downward force on the table.
Yeah, so the block exerts a downward force on the table. Should I draw that in this free body diagram? No, I'll draw it in here, a force on the table. If I want to draw two arrows in the same direction, I'll just make my dot big enough that it can accommodate another straight down arrow. All right, so this is a normal force by what object on what object? Block on the table. Block on the table, okay. And now I'm going to ask one more time, how big should this upward normal force by the ground on the table be? Griffin?
As big as FG plus FL.
Yeah, as big as both of those combined. Cool. I am going to take my red pen and circle a Newton's third law pair of forces. Which am I going to circle? Anyone I haven't heard from in a little while? Which are the Newton's third law pair in these forces? Jay?
So one pair would be the two forces acting on the block.
This is a Newton's third law pair with that?
Yes.
I'm going to disagree. The Newton's third law pair to a force by the table on the block is a force by what on what?
Table on block.
Sorry, the Newton's third law pair to the table on the block force is a force by what on what?
Table on the block.
I would say block on the table. Here's table on the block.
Yes.
And so Newton's third law is A on B and B on A. So it's block on the table. It's this one. Is this a Newton's third law pair to this one? No. What is the Newton's third law pair to the Earth's gravitational force on the block? Jonathan?
Block's gravitational force on the Earth.
The block's gravitational force upwards on the Earth. Not pictured in any of these free body diagrams. What free body diagram would the Newton's third law pair to that appear in? The Earth's free body diagram, and we're not drawing that here. So not all forces that balance, or not all forces that have the same magnitude and go in opposite directions are Newton's third law pairs. Yeah, I think that's more or less what I wanted to say. Let me just check. Yes, yes, yes. We talked about that. Yes. Great. Newton's third law. That's it.